So the first part of this lesson will be using KAs to solve questions with acids, and then we'll roll into basis. That'll be a much smaller lesson because almost everything's the same except for the fact you don't have KB, so I have to teach you how do you turn a KA into a KB. Okay. So we're only looking at weak species. None of this would work with a strong because its Ka would be infinitely big, it would be quantitative, it'd be Chem 20. So we're going to be looking at weak acids and using K values instead of percentages. The equilibrium expression and how we write the balanced chemical equation must be a weak acid transferring a proton to water in order to use that value. So it cannot be a weak acid to ammonia. That's a different weak base. Okay, it's got to be to water. That's the only format. So generically, we're always going to see this layout. HA is meant to represent whatever acid we have, a weak acid. It has to be transferring that proton to water as our Bronsted-Lowry base. We're always going to get hydronium as the conjugate of water. And then we get whatever's left over from the acid, which I'm summarizing as A-, which is typically an anion, which is one reason I use the letter A. It doesn't have to be negative, and most of the time it's a negative ion. You will sometimes get questions, here's an unknown acid. Do the calculations. And students are like, how do I write an equation? If I don't know the acid, use HA. You can write this equation, build an ice table, put all the numbers in, and then maybe figure out what acid you have at the end once you know its K value. Okay. The equilibrium law expression is always going to have the same format because the equation has to have the same format because of this definition of K, of our K, to get our Ka values. So Ka is always going to be in the format of hydronium concentration times whatever that conjugate base is of our acid, which I'm calling A-. Okay. It doesn't have to have a charge of -1. It'll have whatever charge the conjugate happens to have. Okay. But using this HA, that's neutral, A would be minus. On the bottom, we're going to have our acid concentration that's left over at equilibrium, which is often very, very, very small, often the same as what we started with, and then we're always going to be dropping water. So this is always the pattern for these questions. And they're always 1 to 1 to 1 to 1. So no squares or powers to worry about. Okay. So in terms of problems, you don't have as many options as you did in chapter 15, where sort of everything was wide open, KC, which is generic. Okay. We're still going to have those I and E questions. What do we do with an I when we have an I and E? Is that when we use the X, or is that when we solve it? Or yeah, you can just solve your whole ice table. You're going to complete that column. You've got I and an E. You can put in the C, propagate your C's, and then fill in all your columns. So that's one option for our acid-base questions. The other option is an I and a Ka value, and that's when you have to use the X. Okay? And you've practiced that skill, and these will be easier because you'll have no powers. Okay? Just realize this is in your data booklet. So these questions are the ones that once you get used to it, they're easy, you'll rock them, you'll have high success. But a student who hasn't practiced a lot, is a bit weaker, they'll go and say, all I have is an I value, I don't know what to do. That's in your data booklet, and you need to put a variable in and solve for it. Okay, so I'm going to do 2 questions, one of each format, and then we'll see what's different about KBs. So determine the Ka for 1 mole per liter acetic acid, and the pH is given. And then I've set this up. I've written the Bronsted-Lowry equation for acid plus water. producing hydronium, and acetate is the name for that conjugate. So there's the acid, there's the conjugate of the acid, acetate. Our other conjugate pairing is the hydronium water pairing. I'm going to use moles per liter for my ice table. So I'm going to start filling in what I know. We have 1 mole per liter of acetic acid. Okay? This is a reactant. It's not stated, but for reactants, you're going to treat the data as I's. Okay? Products, you treat them as E's when it's ambiguous. Okay? So that is 1.00 moles per liter at the beginning. Now, when we get to pH, or if you were given a pOH value, that would be fine, because you could turn pOH into pH if it was given to you. If you're given a pH value, that is always done at equilibrium. It's actually impossible to get a pH value initially. Acid-base reactions are so fast, there's no way you could take a pH measurement before this reaction has occurred. It's fractions of a second. Okay, so biggest part of this lesson is this, that we have to use that somehow to get an E value. Okay? We need to decode that, and you learned that last year, and we reviewed it this week. Okay? pH we can use to decode it into hydronium at equilibrium. So that's what I'm going to do. So the concentration of hydronium is 10 to the negative pH. So 10 to the negative 2.38. Now I switched colors to emphasize decimal places in pH is sig figs when you go back to a standard number. So the only significant figures are the 3 and the 8, 2 of them. Okay? Now you would carry more than 2 sig figs through your work, but this only has 2. We're down to 2. 0.0042 moles per liter. Okay, there were no units whatsoever here. I've not left any out, and they just magically turn into moles per liter. That's the convention. Okay. So I'm just showing to, ideally keep them all in your calculator round at the end. So at E, we have 0.0042 moles per liter of hydronium. So, and I plug that right into the E value. Okay. Now, right away, you may not see, well, the I and the E don't match right now, but I'm going to add in, we would assume products would be 0 at the beginning, and there we've got our I and our E. And now I can just start filling out the whole ice table. So we had to have made 4.2 millimoles per liter. Well, we would have had, everything's 1-to-1. So I'm going to fly through this. Every determination of a change is multiply by 1, divide by 1. So it's going to be the same number all the time in this acid-base section. Not in chapter 15, but in acid-base, it's always going to be the same. And we're seeing what we often see in acid-base is that the change is so small, it's barely even really affecting that original concentration. But I can do the math, and I'll round at the very end. Okay. So 0.996. I know there's an extra sig fig there, but I'll round to 2 at the end. That number's filled in, and that number's filled in. So we got all our E's. I'm going to plug it in and solve it. Again, you're doing a test or diploma. Try to leave all those digits in your calculator. Okay? Don't round all the way through because you can easily be off a little bit by over rounding. I don't remember if I kept all of these in my calculator or whether I used that for my calculation. Now, I'm going to throw in the units just to emphasize, A, they're good to put in, and B, they're not going to cancel here. But we're supposed to drop them because we dropped the water from the equilibrium law expression. Their units disappeared. We end up with moles squared per liter squared divided by moles per liter. They don't cancel, but you have to leave them out. And I got 1.7 times 10 to the minus 5 unitless. That's our Ka. So we solved it. So that's the first strategy, very similar to before. Simpler math, simpler layout because of the 1-to-1 ratio. You just have to take pH and decode it. Last thing, your diploma will never ask you to solve for a Ka that's on your table. You might get a homework question, solve for Ka, and you're like, oh, it's right there. That's not solving for. If it says calculate, solve for, you've got to use the data and solve for it. Okay, it's not uncommon on a quiz sometimes. I'll pick something in the table, say solve for the Ka, and then do a percent error compared to the accepted value. Okay, and you can't just, don't pull the accepted value and say, hey, I know what it is. That's not calculating. Okay, so that's the first format without the X. The second format is the I and a K value. And we're going to have to use a little bit of our equation writing skills to get this started. Determine the hydronium concentration for a little under of 1/3 of a mole per liter solution of ammonium chloride. The question doesn't even tell you if you have an acid or a base. And when you're doing a quiz or test, you may not be told whether you have an acid or a base, whether it's a Ka or a Kb type question. This is ionic. Everything ionic in Chem 20, you're going to treat as soluble and break it up. So this is going to give you ammonium, and it's going to give you chloride, and then you've got to figure out which one is an acid or a base. We will not give you a species where one's an acid, one's a base. So hopefully you'll recognize that chloride is not an acid or a base. Yes, it's on your table, but it's a conjugate of a strong acid. That only leaves ammonium as a possibility, which is quite low. It's 4 up from water on your table, and you've got the K value right here on your table to use. And then you have to think of, well, what's the Bronsted-Lowry equation with ammonia? And it has to be ammonia and water when we use K values. And there's no other bases but water in there. So if you did the 5 steps and put ammonium, chloride, and water on a list, you would generate that as your acid-base equation. So I know few are still writing, but I'm going over and getting the Ka value right away. So ammonium ion, 5.6 times 10 to the minus 10. It's like less than a billionth. Very small K value. X is going to be not just small, but really tiny in this case, our change will be really tiny. So I'm going to, what else can I do to get started? Well, my products would be 0. You don't have to X out water, but you at least need to realize you don't have to do anything with water. You're dropping it from calculations. So I wouldn't even think of it. Okay. And now you're like, what can I do? Well, I've got an I, I've got a Ka, I'm going to have to put an X in and build my ice table from there. I should have put liquid water. That's my error. So that should have been an L. So the X's are going to be simpler now. It's always a 1-to-1 ratio. So all of these are going to be 1X all the time. We just have reactants go down, products go up. Now you've got 2 times where you could articulate that you're going to do the assumption. You could right now, okay, I'm just going to star this because I'm not going to write it out. I'm going to say it orally. Okay, Ka is less than 10 to the minus 3. X is going to be really, really small, so this is going to be very close to the very starting material. So I put a little tilde. That's going to be approximately 0.300. I'm dropping the X at that stage for the sake of my calculation. If I don't, you get a quadratic, and you have to use the quadratic formula to solve it. It'll work, and you'll get the exact same answer as you would if you did the assumption. So Ka equals concentration of ammonia, which is that guy. So on the top, we're going to have X and another X. You're going to see this X squared all the time. So I'm just collecting my X's right away. On the bottom, we have the original concentration. Now I'm going to skip a few math steps. Cross multiply, and then you'd have to square root both sides. So I'm going to just carry those out simultaneously. 1.3 times 10 to the minus 5. Now, unit analysis would not give you moles per liter. Again, because we dropped water, it's going to mess it up, but you have to realize that's the appropriate units. It's just moles per liter, which is not the answer. X will never, ever be the answer. Okay? So now we got to figure out, well, what is the answer? Sometimes it's X or 2X or X squared, or maybe if it's pH, we have to do a bunch of work. And our question is hydronium concentration, which is X. So just 1X, so hydronium is that concentration. And a likely question or variation would be, what's the pH instead of what's the hydronium? And you take the negative log of that. Okay. So that is how to deal with Ka type questions. Okay. And Kb is going to be very similar. I just have a couple slides to talk about the slight variations we have to do if it's a base in water instead of an acid in water. Okay. And then you'll have some practice time. Okay. So base equilibrium, Kb's. And this is where in AP, we're going to do some different types of equilibrium, but they're not really going to be harder. We'll go to KSP for solubility product, but all the fundamental skills are the same. So the AP unit that's next is almost easier than this unit because it's building on the same skills. So like an acid, we've got that Kb is calculated by a weak base in water. Okay? It cannot be any other weak acid. An example, what if you had ammonia and you wanted to do some calculations? That is a base. So we're going to have to do the Bronsted-Lowry equation for that base in water. So I start with my base. Water must be the acid. The base by definition is a proton, what, acceptor or donator? Acceptor. And that helps you predict the conjugates. So we get ammonium. So ammonia is NH3, ammonium is the ion. And that ion is in your polyatomic ion table. And we get a hydroxide, of course, because we have a basic equation instead of an acidic equation. And then I'm going to roll right into an example. I'm going to use that same ammonia that I just used in my intro example. Determine Kb when a quarter of a mole per liter, when you have a quarter of a mole per liter aqueous ammonia solution. And we're given the pH of this solution, and it's a basic pH as we would expect, above 7. So we need the equation for ammonia plus water. I'm going to use mole per liter. I'm always use mole per liter units. Care about water. Our products would be 0 at the beginning. We wouldn't have any before the system has gone to equilibrium. Now we've got to use that pH somehow. Okay. Same as before, a pH value is always at equilibrium. I don't want the hydronium concentration. That's useless to me. There's no hydronium in this initial equilibrium. Okay. I want hydroxide. So I don't want to use pH. I need my POH. And then I can get my hydroxide concentration. So pH and POH sum to 14. I'm leaving out, I'm just doing this part orally. If you take 14 minus your pH, you'll get your POH. 2.68 is the POH. And that's useful because that will let us get our hydroxide concentration. 10 to the negative 2.68. Okay. I'm color coding those decimals again to highlight the significant figures. Now, if you round sig fig wise, that'd be 2 sig figs. Now, I wrote down and just carried forward at least one more, so 208. But I know there's an extra sig fig here. But I'm going to carry that extra one through and show it this time. Again, ideally, you're just leaving all those digits in your calculator. On a quiz, you'll write down the rounded version, but try to keep them all, particularly if you have a graphing calculator. And that's really the only difference. Now I'm going to finish exactly the same as I did before. So is there any questions about that flow I did from pH to POH to hydroxide? So that's the change for hydroxide, and that'll be the same change for everything. Now, I've talked about the changes being small and being able to drop them for the initial acid or base, but we only need to do that when we have an X and we don't want to do the math. If I know the small amount, well, there's no reason not to use it and do that tiny change. Okay, so only drop it when it's a variable and you're trying to simplify your math. So I'll solve KB and then we'll compare it to the number in the table. So KB equals I get 1.8 times 10 to the minus 5. And this is where I was limited to 2 sig figs. And luckily on your diploma, and you'll see it on our unit test, all the numeric response questions, they tell you how many digits to report. So when you get your diploma, turn off your sig fig brain and just do what they tell you. You don't have to worry about it. Okay? As a teacher, it annoys me a bit. Sig figs are not assessed on your diploma whatsoever. It's all numeric response, multiple choice. Okay? They've never put a question with 2 answers out of the same. One is 2 sig figs, one is 3. I've never seen that. They never do that. So it's really only for AP, and it's for your lab skills, your labs, that you'll get more assessed on your sig figs. Okay? And you should do it on your written stuff for your quiz, because the diploma isn't godlike and our only goal. And our goal is to learn for post-secondary. Not anally picky. Their scores tend to be, if something's worth 2 marks, you get 2, 1, or 0. So if you're off by 1 sig fig, you might still get the 2, but you still want to learn to do it right. But they're not taking quarters off. AP doesn't take like a quarter or a tenth or anything off a question. It's sort of 0, 1, 2 type of marking. So how does this compare to our data booklet for next to ammonia? Am I anywhere near the value in the book? So I got 1.8 times 10 to the minus 5. We could find ammonia. It's right in here. There's ammonia, and the value is not anywhere close. 5.6 times 10 to the minus 10. Why is that number nowhere near? Have I made a mistake? Perfect. This is Ka. This is not what I solved for. I solved for Kb. Now we can convert that into a Ka. Or sorry, we can convert that into a Kb, and that's what I want to show you how to do. So make sure, a common mistake is a student kind of loses track of Ka and Kb, and they get a K, and they don't, they just sort of lose that the importance of that subscript. So Ka versus Kb. Okay, this is, the formula is not given. Okay. This all goes back to the auto-ionization of water. Okay. The acid equilibrium constant, if you multiply it by the conjugates Kb, you get Kw, the water ionization constant. Now this is only true for conjugates. Okay. So you have to have an acid slash its conjugate, okay, where a proton has been lost. And this lets you relate the Kb of the acid to the conjugate base. But you really got to watch out, and you'll get tested on this. It's got to be the same row. And you've got all those amphiprotic species that you have to make sure you don't sort of interpret that statement. Something like hydrogen carbonate is here as an acid. Okay. And if I took that Ka value, HCO3, I would predict CO3 2 minus this Kb. But a test could easily throw in H2CO3 and ask you, it'd be incorrect, is this the Kb for H2CO3? But that's not the conjugate. That's adding an H to this. It's got to be the acid. You take away an H, you get that species. You can predict that Kb. Okay. The amphiprotic species, HCO3, shows up there as an acid. It shows up higher up as a base. Or is it lower down? There it is. So there's HCO3 twice in 2 different conjugate pairings. Okay? So you just need to make sure you have the right pairing, you set it up right. Okay? If it's not amphiprotic, it's pretty straightforward. If it is amphiprotic, it's in the table twice. You have to think of it, are you talking about the acid or the base format? Okay? So often you'll need to calculate Kb. If you had a question, you need the Kb, you're given the I of a weak base, and you need its Kb, you've got to do this and solve for it from the table, finding the right conjugate row. Take your Kw, divide by Ka, okay? And you can take this and convert it. So we'll do that for ammonia. We just solved for the Kb for ammonia. Okay? Let's turn this Ka into a Kb and see how close it works out. So 1.00 times 10 to the minus 14, that's a unitless number. Divide by the Ka. Okay? So I'm looking up the Ka for this guy to predict the Kb for its conjugate that we just solved for. The Ka in the table is 1.8 times 10 to the minus 5. No, I think I wrote that. And I can solve for the Kb. I didn't write it down, but it's very close to 1.8 times 10 to the minus 5, what we predict. I think it might actually be 1.7. So the value we got on the other side is very close. Okay? So Kb's, you're going to be doing this all the time to solve your base questions. Okay? Figuring it out. I'm going to stop there. So some questions you can work on. There's also a lot of workbook practice. Okay? Students tend to like the workbook. Either one is fine. I just don't have the page numbers off the top of my head of where to practice there. As a student, I would practice a few Kas, try to get it down, and then it's the Kb's where you're probably going to make errors. I would expect an incredible high degree of success of Kas, and maybe move on. Don't do every single one once you feel you have that comfort. Okay. If you can get through the Kb questions, the Kas are conceptually simpler.